Hello everybody. Today I want to discuss how to calculate the value at risk under the assumption of a log-normal distribution. Of course, one may ask, why do we have an interest in using log-normal distributions? And why do we use a log-normal probability density function instead of a normal one? The answer is rather easy, and it's because the empirical evidence shows that many asset prices are distributed log-normally. Well, first of all, let me show which are the main characteristics of a log-normal distribution. Here you can see the probability density function and the cumulative density function. But perhaps the most important things are the moments. The first moment of a log-normal distribution is the following, and it is equal to the natural logarithm of the expected value of our random variable x, which is our end-of-year portfolio value, minus 1/2 times the natural logarithm of 1 plus the variance of x divided by the expected value of x squared. The second moment is equal to the natural logarithm of the variance divided by the expected value squared plus 1. I will come back later on this point. Well, now, suppose to have a single asset whose mean return is equal to 15%, its annual standard deviation equal to 20%, and an initial value equal to 100 million euros. We have to answer two questions. What is the probability that the end-of-year value is less than 90 million euros? And what is the value at risk? As I did in my previous example, I will use Mathematica software, a very useful tool. And the syntax of Mathematica to calculate the value at risk is the following. I open the normal distribution toolbox, statistics normal distribution, and I plot the probability density function, which is written in this way. As you remember, before I wrote the first moment, and I insert our real values, and I obtain this this stuff, and I plot this distribution in this interval 0-80, and what I obtain is basically this. Of course, as you can see, this distribution has rather a funny shape, which is basically given by the characteristics of a log-normal distribution. Secondly, I want to calculate the probability that the end-of-year value of the portfolio is less than $90 million. And I do this by writing the following expressions, which gives the following answer. Probability is equal to 11.96%. Now, I want to calculate the value at risk, and I do this in two steps. First of all, I write the function with clear row log-normal VAR, and then I set the function log-normal VAR, which is a function of mu, sigma, and x, three variables, and which is also equal to 100, our initial values, minus the quantile I want to calculate. Secondly, I plug the values, the real values, of our mean, standard deviation, and the percentage in the function, assuming that our confidence interval is equal to 99%. And so I write that the log-normal VAR is function of 0.15, 0.20, and 0.01. and the value at risk is $28.485 million, which is our value at risk. Now, if I want to compare what I obtain by using a log-normal distribution with what I obtain with a normal distribution, I do basically the same, this time using a normal distribution. I obtain the probability that the end of the year portfolio value is less than $90 million, equal to 15.86%, and a value at risk equal to $31.527 million. I can draw two conclusions. The first one is that the log-normal distribution gives higher probabilities that the end of year portfolio value is less than a given level. And in fact, if you compare the two values, you can see that the value obtained under a log-normal distribution is lower. But also, I obtain lower value at risk, because again, if you compare the two values I obtain by using the log-normal distribution and the normal distribution, I obtain that the value at risk obtained by using the log-normal distribution is lower.